Hello and welcome to lecture number 18 in the course Computer Graphics. We are currently discussing the 3D graphics pipeline, that is the set of stages that converts an object description to a 2D image on a computer screen. What are the stages? Let us quickly recap. There are 5 stages as shown here: object representation, modeling transformation, lighting, viewing pipeline and scan conversion. And also it may be recalled that each of these stages work in a specific coordinate system. For example, object representation works in local or object coordinate system. Modeling transformation works in local to world coordinate system. It is basically a transformation from local coordinate to world coordinate system. Then lighting or assigning colors to objects happen in world coordinate system. Then the viewing pipeline, the 4th stage, actually consists of 5 substages, and there is a variation in coordinate system where they work. For example, the first stage, viewing transformation, is a transformation from world to a view coordinate system. Then clipping, the second stage, works in view coordinate system. Hidden surface removal, third stage, works in view coordinate system. Projection transformation, which is again a transformation that takes place between 3D view coordinate to 2D view coordinate system. And window to viewport transformation, the 5th substage of the 4th stage, takes the object description from view coordinate to device coordinate system. The last stage, scan conversion, essentially is a transformation from device to screen or pixel coordinates. So far, among all these stages and substages, we have covered 3 stages, the first 3 stages in our previous lectures. First one is object representation, then geometric transformation and lighting or assigning colors to the objects. Today, we will start our discussion on the 4th stage, that is viewing pipeline. Now, let us start with some basic idea of what we mean by the viewing pipeline. Let us start with a background knowledge. So, up to this point, whatever we have discussed in our previous lectures, we learned how to synthesize a realistic 3D scene in the world coordinate system. So, we started with the object definition stage or object representation stage, then we put together the objects in the second stage, modeling transformation stage, to construct a world coordinate scene, and then in the third stage we assigned colors in the world coordinate description of the scene to make it look a 3D scene. So, the knowledge we have gained so far is good enough to explain how we can create a 3D realistic scene. Now, that is not the end of it. So, we need to display this scene on a 2D computer screen. So, that means essentially we need a projection of the scene on a 2D screen from the 3D description. And this projection need not be of the whole scene, it can be a part of the scene also, which is the most common way of looking at it. We usually talk about a portion of the overall 3D description to be projected on a screen. Now, this process of projection is actually similar to taking a photograph. So, when we take a photo, the photo is basically a projected image of a portion of the 3D world that we see around us, that we live in, and this projected image is on the photographic plate or a camera screen. So, when we are talking of displaying a 2D image on a computer screen, essentially we start with a 3D description of the scene and then we want to simulate the process of taking a photograph. Now, this process of taking a photograph is simulated in computer graphics with a set of stages, and these stages together constitute the fourth stage of the graphics pipeline, that is viewing pipeline. What are those stages? The very first stage is to transform the 3D world coordinate scene to a 3D view coordinate system or reference frame. Now, this 3D view coordinate system is also known as the eye coordinate system or a camera coordinate system. And this process of transforming from 3D world coordinate to 3D view coordinate is generally called the 3D viewing transformation. So, this is the first stage in the 3D viewing pipeline. Then we project the transformed scene onto the view plane. So, this is the projection transformation. So, first comes 3D view transformation, then comes projection transformation. Now, from the view plane after projection, we perform another transformation. The projection is done on a viewport on the view plane. Now, from there we transform the objects to the description on a device coordinate system. So, when we perform projection transformation, we essentially transform on the view plane. Now, that area where the image is projected is called window. Now, from this window we make a further transformation. From the window, the object descriptions are projected onto a viewport which is on the device coordinate system. So, we perform window to viewport mapping. So, this is the third stage of the viewing pipeline that we are considering in the fourth stage of the graphics pipeline. Now, these three are the basic stages in the 3D viewing pipeline. Along with that, there are couple of operations, namely clipping and hidden surface removal, which together constitute the entire fourth stage of the 3D graphics pipeline, namely the viewing pipeline. And we will discuss each of these sub stages one by one. So, let us start with the first substage, that is 3D viewing transformation. Now, in order to understand this transformation, we need to understand how a photograph is taken. So, there are broadly three stages through which we capture a photo. First, we point the camera to a particular direction with a specific orientation, so that we can capture the desired part of the scene. Then we set focus and finally we click the picture. These three are broadly the stages that we follow when we capture a photo. Now, among them, most important thing is focusing. with focusing we get to know, or at least we can estimate the quality and the coverage of the picture that we are taking. So, focusing constitute the most important component of the overall process of capturing a photo. Now, in order to set the focus, what we do? We essentially look at the scene through a viewing mechanism that is provided in the camera. Typically, while we try to set focus, we do not look at the scene with our bare eyes, we look at the scene through the viewing mechanism provided in the camera itself, and accordingly we set our focus. Now, this is important. So, we are not looking at the scene with our bare eyes to set focus. Instead, we are setting focus based on our perception of the scene obtained by looking through a viewing mechanism provided in the camera. So, we are looking at the scene through the camera instead of looking at the scene directly. So, this is very important consideration. If we are looking at the scene directly, that means we are looking at the scene in its original coordinate system, that is what we are calling world coordinate system. So, when we are looking at the scene directly, we are looking at it in its world coordinate reference frame, world coordinate system. However, if we are looking at the scene through a viewing mechanism of the camera, then we are not looking at the scene in its world coordinate system. Instead, we are looking at a different scene, one that is changed. It is important to note that a changed scene, and the change took place due to the arrangement of lenses in the camera, so that we can estimate the quality and coverage of the photo to be taken. So, here we are not looking at a world coordinate scene, we are looking at a scene that is changed from its world coordinate description due to the arrangement provided in the camera viewing mechanism. So, then what happens? When we are taking a photograph with a camera, we are actually changing or transforming the 3D world coordinate scene to a description in another coordinate system. This is the most fundamental concept to be noted to understand how computer graphics simulates the process of taking a photograph. So, when we are looking at a scene to set focus through the viewing mechanism provided in a camera, we are actually transforming the world coordinate scene to a different coordinate system, and this coordinate system is characterized by the camera parameters, namely the position and orientation of the camera. This needs to be carefully noted. So, this new coordinate system, we generally call it view coordinate system, and the transformation between world coordinate system and view coordinate system is the viewing transformation, which is the first substage of the viewing pipeline. So, essentially we are trying to simulate the photo taking process, and the first stage in it is to transform world coordinate description of a scene to the view coordinate system, which simulates the process of looking at the scene through a viewing mechanism provided in the camera. So, to simulate this viewing transformation or to implement the viewing transformation, we need to do two things. First, we need to define the coordinate system, and second is we perform the transformation. So, first we define the coordinate system and second we perform the transformation to simulate this effect of looking at the scene through camera. Now, let us go one by one. First, we try to understand how we set up the viewing coordinate system. This figure shows the basic setting that we will be considering here. So, on the left side here is the actual world coordinate scene. So, this is the cylinder is the object in a world coordinate description defined by the three principal axes x, y and z, and then this is the camera through which we are looking at the scene, and this view coordinate is characterized by the three principal axes x view, y view and z view. Although the more common notation used in graphics is u, v and n to denote these three principal axes of the view coordinate system rather than x, y and z. So, in subsequent discussion we will refer to this view coordinate system in terms of this letter notation, that is in terms of the principal axis u, v and n. So, the question is, how do we determine this principal axis which defines the viewing coordinate system? You may note here that n corresponds to z, v corresponds to y and u corresponds to x. So, let us try to understand how we can determine the three principal axes to define the view coordinate system. So, first thing is to determine the origin of the view coordinate system where the three axes meet. Now, this is simple. We assume that the camera is represented as a point and the camera position is the origin denoted by O. So, the position of the camera is the origin, where we are assuming that the camera actually is defined as a point, a dimensionless entity. Now, when we try to focus our camera, we choose a point, as we have already mentioned before, in the world coordinate system, and we call this the center of interest or look at point, as shown here. So, this is our camera position and this one is the look at point. As of now, you may note that both are defined in the world coordinate scene. So, with these points we can define vectors. So, this will be the origin vector and this will be the look at point vector p. Then using vector algebra, what we can do is we can define n. As you can see, n is the normal of the plane. So, we can define n to be O minus p, where each of these are vectors. That is the simple vector algebra we can use. And then we normalize n to get the unit basis vector n cap, which can be defined simply as n by mod of n. So, then we got one basis vector n. Next, we specify an arbitrary point, that is denoted by p up, along the direction of our head while looking through the camera. This we call the view up point along the view up direction. So, the direction along which our head is oriented while we are looking at the seen through the camera. Essentially, this is the head up direction. Now, with this point we determine the view up vector, this vector V up as a difference of these two vectors, as you can see from the figure here. This is again simple vector algebra, and once we get this V up vector, then we can get the unit basis vector V cap in the same way by dividing the vector with its length, which is a scalar quantity. Now, we got two vectors, then two basis vectors n and v. Now, if we look at the figure, you can see that the remaining vector u is perpendicular to the plane that is spanned by n and v. So, if this is the plane, then u will be perpendicular to this plane. Then we can simply use the vector algebra again to define u to be a cross product of v and n, v cross n. Now, since both n and it should be v are unit vectors, so further normalization is not required and we get the unit basis vector u by this cross product. So, then in summary what we have done, we assume that few things are given, three things. One is the camera position or the coordinate from where we can define the origin vector O, then view up point and corresponding view up vector we can define, and finally the look at point P and the corresponding vector. Then based on these information we perform a three-step process. First we determine the unit basis vector n cap using simple vector algebra. Then we determine V cap again using simple vector algebra, and finally we determine u as a cross product of the earlier two vectors that we have defined in the first two steps. And following these stages we get the three basis vectors which define our viewing coordinate system. Now, once the coordinate system is defined, our next task, that is the second part of the process, is to transform the object definition from the world coordinate system to the view coordinate system. Let us see how we can do that. So, in order to transform, we need to perform some operations. To get an idea, let us have a look at the figure here. So, suppose this is an arbitrary point in the world coordinate scene and we want to transform it to the view coordinate system defined by the three vectors n, u and v. Now, let us assume that the origin is defined with this point having the coordinates mentioned here, and the three basis vectors are represented as shown here. These are the x, y and z component of the basis vectors, and this representation we will follow to formulate our mechanism to transform any arbitrary point in the world coordinate scene to a point in the view coordinate system. So, what we need? We need transformation matrix M. If you recollect, in the modeling transformation stage we said that any transformation can be represented in the form of a matrix. So, we need to find out that matrix which will transform a given point to a point in the view coordinate system. And how we do that? Again, if you recollect our discussion from the lectures on modeling transformation, what we did? We multiply the point with the transformation matrix to get the transformed point. So, this is the transformed point which we will get by multiplying the original point with the transformation matrix. And this transformation is actually a sequence of transformations that are required to align the view coordinate with the world coordinate. In a most general setting, they are not aligned, like in the figure shown here, there is slight difference in orientation between the two coordinate systems. So, we align them and then perform the transformation. Now, in order to do that, we require two basic transformation operations: translation and rotation. The idea is simple. So, we translate the origin to the world coordinate origin and then rotate the system to align with the world coordinate system. So, this translation and rotation will constitute the sequence of operations we need to transform between the two coordinate systems. Now, first thing is we translate VC origin to world coordinate origin, and this is the transformation matrix which is same as we discussed earlier with the corresponding x, y, z values replaced here. Next is rotation. Now, the rotation matrix is shown here, we will skip the derivation, it can be derived. But for the time being, let us just note the rotation matrix. So, this matrix will align, if applied, this matrix rotates the viewing coordinate system to align it with the world coordinate system. And since we performed first translation and then rotation, so we will follow the right to left rule to combine the two transformations to come up with a composite transformation matrix. Thus, we will have to write them in this sequence: T first and then on the left side is R, and we take the product of these two matrices to get the composite matrix, and then we multiply this matrix to the point to get the transformed point coordinates. Let us try to understand this process in terms of one example. Consider this setting. Here there is a square object defined with its vertices A, B, C, D, and then we have a camera located at this point 1, 2, 2, and the look at point is center of the square object here, that is 2, 2, 2. It is also specified that the up direction is parallel to the positive z direction. Then, given this specification, let us try to calculate the coordinate of the center of the object after transformation to the view coordinate system. So, originally it is in the world coordinate system, it is 2, 2, 2. Now, after transformation, what will be the coordinate? Let us try to follow the steps that we have just discussed. The first thing is we determine the 3 unit basis vectors for the viewing coordinate system. Now, the camera position is defined O, that is 1, 2, 2, as you can see here. look at point P is defined at the center of the object, that is 2 2 2. So, then we can calculate the vector n as O minus P, which is minus 1 0 0. Now, it is already a unit vector, so no need to do any further operation. So, we already got the unit basis vector n cap. Now, it is also mentioned that the up direction is parallel to the positive z direction. Therefore, we can directly determine that the unit basis vector along the up direction v cap is basically the unit basis vector along the z direction only, that is 0 0 1. We do not need to do any further calculations. So, this as you can see is another way of specifying the up vector. You tell the direction in terms of available basis vectors or in terms of a line rather than specifying a point. So, there are different ways of specifying the up direction. Anyway, so we have already found out two basis vectors n and v. Then we take a cross product of these two basis vectors to get the third basis vector u cap, which is 0 1 0. So, then we found the coordinate system, view coordinate system as defined by the three unit basis vectors n, u and v. Next, we compute the transformation matrix M, which is composition of the translation and rotation matrices. Now, we have already noted earlier that the translation matrix is represented in this way, where we use the coordinate position of the origin since it is already given to be 1 2 2. So, we replace it here to get the translation matrix in this form. Again, we already know the rotation matrix, which is in terms of the vectors which define the coordinate system, and we already have determined these vectors. So, we replace those values here. So, n cap is minus 1 0 0, u cap is 0 1 0 and v cap is 0 0 1. We already have determined these. Now, we replace these values. This is for u, this is for v and this is for n to get this rotation matrix R. So, then we multiply these two R dot T to get the transformation matrix M shown here. Now, we have determined M, then we multiply M with the original coordinate to get the transformed coordinate, and note here that it will be in the homogeneous coordinate system, but with a homogeneous factor 1. So, we do not need to do any change. So, after multiplication what we get? We get that the coordinate of the transformed point is 0 0 minus 1 in the view coordinate system. So, that is our transformed point in the view coordinate system. So, in summary, today what we discussed? So, we are discussing the fourth stage, that is viewing pipeline, which is essentially simulating the process of capturing a photo. Now, this process consists of multiple stages. Broadly, there are 3 stages. First is a transformation from world coordinate description of an object to a view coordinate system. Second is from view coordinate system to projection on a view plane, and the third is from the view plane a transformation to the device coordinate system. Among them, we discussed the first major stage, that is transformation from world coordinate description to a view coordinate description. There we have seen how we can define a view coordinate system in terms of its 3 principal axes u, v and n, and how to determine these 3 principal axes given the information of the camera position, the view up vector and the look at point. Once these 3 are given, we can define the 3 principal axes for the view coordinate system, which in turn gives us the system itself. Then once the system is defined, we determine a transformation matrix, which is a composition of translation and rotation, to transform a point from world coordinate system to the view coordinate system. We achieve this by multiplying the world coordinate point with the transformation matrix to get the transformed point in the view coordinate system. We may note here that here also we are assuming a homogeneous coordinate system. However, the homogeneous factor is still 1, so we do not need to do any further change in the computed coordinate value. In the next lecture, we will talk about the second major stage in this viewing pipeline, namely the projection transformation. Whatever we have discussed today can be found in this book, and you are advised to refer to chapter 6, section 6.1 to learn in more details the topics that we have covered today. Thank you and goodbye.